In this tutorial, we're going to talk about thermal expansion. We have, for instance, linear expansion, and suppose that we have any given, I don't know, a bar, for instance, which is at a certain temperature, which is initial. And if we apply heat, then this will expand linearly into a final temperature, and this difference in length is what is going to be called the linear expansion. So this difference in length is going to be equal to alpha times the initial length of this rod, which is, for instance, this one, times the change in temperature. Or, for instance, final minus initial length is going to be equal to alpha times initial length plus the difference in temperatures. This alpha is called the linear expansion coefficient, and is what it depends on the material. This linear expansion coefficient, which depends on the material, is measuring 1 over degrees Celsius, or 1 over Kelvin, or 1 over degrees Fahrenheit. Since we are having, for instance, delta T as a factor of alpha, then 1 over Kelvin is going to be equal to 1 over degrees Celsius, but not equal to 1 over degrees Fahrenheit. We have to use the fact that at delta T in degrees Fahrenheit is going to be equal to 1.8 delta T in Celsius in order to turn from Fahrenheit to Celsius or Kelvin. These expansion coefficients are going to be any given number times 10 to the minus 6. So they are going to be very small, times 10 to the minus 6. We're going to talk about the superficial change as well. For instance, we're going to take that initial area is equal to the length to the square, such that the final area is going to be equal to the initial length plus its change to the square. And then, of course, if we want a change in the area, which is what we're looking for, we want to state that this is going to be, for instance, the final minus to the square minus the initial. And if we develop this, we're going to end up with expression as like this, for instance, which is developing the square minus the initial length. These two might cancel, and then of course we're going to have 2 initial length delta L plus delta length to the square. Now 2 initial is 2L0 delta L is going to be 2 alpha length initial to the square times delta T, and this term we can neglect it because this is going to be, for instance, alpha to the square, which is, for instance, times 10 to the minus 12. Since the other one was times 10 to the minus 6, it's going to be very, very small. We can neglect it. So at the very end, the change in area is going to be equal to 2 alpha initial area times delta T. And this is the superficial change. We can do the same procedure with the volume, and we are going to get that the change in volume is going to be, for instance, initial length plus delta L to the cube minus initial L to the cube. And if we develop all the terms, at the very end we are going to end up with negligible terms. For instance, initial length to the cube plus 3 initial length to the square delta L plus 3 initial length delta L to the square, which we know that is negligible, plus delta L to the cube, which for instance is even more negligible, minus what we had from previous. We're going to end up with delta V is going to be 3 initial length to the square delta L, or in other case we are going to state that it is 3 alpha initial n to the cube delta t, or we can rename 3 alpha and call this beta, which is the volumetric expansion coefficient, and we can call this the initial volume, such that delta V is going to be equal to beta initial volume delta T. This is the volumetric expansion.